Here we are, another day in math. This is part two of our all of single variable calculus in a single day lecture. Obviously, it's not even close to all of it, just a highlight of some greatest hits. So, we're going to do Taylor series today. Or are they Taylor's series? Let's see what those question marks reveal. Now, the basic claim that I'm making here is about math. But before I get into that, I just need to have a moment. So, bear with me, because I'm really feeling it. I do my research for these videos. I have forgotten quite a few things from math myself, and I keep relearning, reforgetting, relearning. That's just how this whole thing goes, right? But I always want to make sure that I'm understanding the content, actually, like really getting it before I go and teach it. Maybe that just makes sense. I don't know. Anyway, so of course, I go to the Goog and I'm like, Taylor S, because I'm going to search for Taylor series. I want to look for animations, certainly, and just get different explanations and all that. And so I type in Taylor S. You can see where this is going, probably. Uh, so this happens and I gotta complain, right? Because if only people appreciated math the way they appreciate pop music. Now, also to be fair, before like before a legion of Swifties comes after me and cancels me or whatever, I I will say, to be totally honest, Taylor Swift's music is not really my thing, just like genre-wise, but I actually have a huge amount of respect for her as an artist. Like, she actually mostly writes and records and plays her own stuff. Like, she's a real live performer. She is incredibly willing to wade into battle with the evil record companies and stand up for her rights as a creator. So, I actually think she's pretty great. I just personally am not, like, into her music. But regardless, that was my old man moment. Thank you for putting up with me onto the content. Taylor series, not Taylor Swift. So we have our animation here, and you're like, that's a nice animation. What is it showing? Well, what it's showing is that we are summing up some polynomial terms. And as we sum these polynomial terms, so that's the n in the top right, the zeroth order, first order, second order, third order, fourth order, and as we add more and more terms, you can see that the red line, which is the series approximation, gets closer and closer to the blue line, which is the actual function. So we're taking this blue function and we're trying to approximate it really well by adding together a bunch of x plus x squared plus x cubed plus x to the fourth, so on terms. And you're like, why do that? Doesn't that seem harder? I'm going to add a whole bunch of things to a whole bunch of powers instead of just calculating a single function. Well, whether that's easier or harder depends on what the function is that we're trying to approximate and also what computational tools you have available to you. The importance and the necessity of this problem in 2025 is very different than it was in 1525 because we have computers. Uh, so that said, the mission for doing this calculation is really to find these coefficients, the a sub n terms here, where it's like we need to find the values for these things. And then you can write down, I have my x term and my x squared term and my x cubed term, and each of those has some coefficient. So we're taking functions, we are approximating them with polynomials. That's what we're doing here. This is what a Taylor series is. It's finding the polynomial approximation for a non-polynomial function, if there is one. Now, with the finite series, you just don't sum it all the way to n equals infinity. You stop after 3 or 5 or 10 or 20, whatever terms. And this is down to the accuracy of the calculation that you need. If you don't need to be super accurate, maybe you use fewer terms. If you need to be very accurate, you use more terms. So that's the approach here. How we find these coefficients is by doing differentiation on our original function that we're trying to approximate. Here's the formula. So let me just talk through the labeling for a second here. A sub n is our coefficient. N is some uh, non-negative integer, so 0, 1, 2, 3, 4, blah, blah. We have 1 over n factorial, and then we have the nth derivative of the function evaluated at the point that we're expanding around. So let me talk about the logic here for a second. Just why is this reasonable? I'm not going to prove this, but I do want to argue reasonableness. If you have some function, I'm going to go back to the picture on the previous slide. If you have the blue function, look at n equals 1, straight line, n equals 2, parabola, n equals 3, cubic function. And you can see that as we go to higher and higher powers, that we're able to get closer agreement. But why are we doing this thing with derivatives? Well, what we're doing is we're taking the value of the function at a known point, and then we're extrapolating to an unknown point some distance away. To phrase that in a different way, we're saying, how much does my function change when my input variable changes a little bit? That's rates of change. That's what derivatives are for. Except we're not just stopping at first order. We're not just doing a linear approximation and saying, well, my slope is this much, rise over run is that much. And so I'll do dy dx times delta x to find delta y. We're doing additional terms to gain more accuracy, taking into account the curvature and the rate of change of the curvature as we add more terms to the series. So that's what we're doing here. We are looking at how our function changes relative to a known value to extrapolate to a new value. That's why we have derivatives here. Okay. Now, in the labeling, this this little f of n, sorry, not f of n, but f to the n thing here, this does not mean the nth exponent of f. That was hard to say. It means the nth derivative of f. And the indicator here is the parentheses. So f superscript parentheses some number means that number of derivatives of the function. So if I have f superscript parentheses 4, that means fourth derivative. And then you evaluate that nth derivative at the point x equals b. If I combine this recipe for the coefficients with the expression from the previous slide, just put it all together in one place, then it looks like this. This is your recipe. This is how you calculate the Taylor series of any function that has a Taylor series. Now, if the derivatives don't exist, then this breaks. There are also functions that appear well behaved, but that actually do not have a general Taylor series. You might be able to approximate them in a region near a certain point, but there might not be a single series that captures the entire behavior of the whole function. I'll show a picture of that on the next slide. But when there is a Taylor series, this is what it looks like. We take the nth derivative of the function, evaluate it at our point that we're expanding around. We multiply that by x minus that point. So again, this is derivative times change in x, essentially, which is giving us an amount of change in the function. That's the extrapolation part. And the reason we have the 1 over n factorial is that as you take multiple derivatives of the series, you're pulling down those coefficients from the polynomial terms. Like if I take three derivatives of x to the fourth, well, I get 4x cubed, then I get 4 times 3 times x squared, then I get 4 times 3 times 2 x1. That's the factorial thing that's happening here. But as I said, this doesn't always work. Now, part of this is just accuracy limitations. So what I have here, the blue curve is sine of x. I guess it's lavender. The lavender curve is sine of x, and the pink curve is the seventh order Taylor polynomial of sine of x. So it goes up to the x to the 7 term in the Taylor series. And this shows that in the region between negative pi and pi, it's a really good approximation. Near the boundaries, there's a little bit of difference where it starts to diverge noticeably, but it's pretty darn close. So as you go further and further away from the known value that you're extrapolating from, that approximation gets worse the further you go. But also, there are functions that are just pathological. They just don't behave. So here's the natural logarithm. Really, this is log of x minus 1 to be more precise. And you can see that the the Taylor approximation here works really well in a certain region. But as we add more and more terms, the approximation gets worse past x equals 1. It actually has this like divergence to the series. I had to remember the right math word. So just because you can calculate a Taylor series, just because you know how to take the derivatives, doesn't always mean it's a good approximation. This is something that's part intuition, part experience, also just part testing something. Try something, see if it breaks, see if it works. Test against known values to establish whether your computations are valid. Okay, so we're going to look at an example here. We're going to do the exponential function. It's super useful. It's super common. It's also pretty easy because derivatives of exponentials are easy and that's why we love them. Okay, so my question is, what is e to the 2? I want to evaluate the function e to the x at x equals 2. So give or take, it should be 7.5. E is like 2.7. So 2.7 squared. Well, it's somewhere between 2.5 squared, which is 6.25, and 3 squared, which is 9. So I kind of split the difference. This is total mental math approximation here. We know e to the 0, so we're going to expand around that point. We're going to have b equals 0 from that expression earlier. I plug in these values to our Taylor polynomial calculation. So we have f of 0, we have the first derivative at 0 times x minus 0. We have the second derivative times x minus 0 squared. We have the third derivative times x minus 0 cubed. And you keep as many terms as you want. Now, to evaluate this thing, we're going to evaluate it at x equals 2, so we plug in 2 for all of our x's. 2 minus 0 is just 2, real nice. And this is what we are left with. So we'll have 1 plus 2, 3, plus 2 squared over 2. So that's 1 plus 2 is 5. Then we'll have 2 cubed over 6. So that's 8 over 6, which is 1 and a third. I hope I did that right. I'm doing this in my head as we go. So then we have 5 plus 1 and a third. So that's 6 and a third. This is starting to get pretty close to 7.5, actually. If I try to do one more completely unscripted, so that's 2 to the fourth, which is 16 over 24, which is that 3/4? No, that's 2/3. Um, so then that gets us up to 7, 1 plus 2 plus 1 and a third plus 2/3. So you can even tell that these numbers are converging. It's getting closer to that 7.5-ish number. And the more accurate you want to be, the more terms you keep. So why do we care? Always want to answer this question. When we're working with functions of numbers and we're doing these things computationally, as was discussed in previous lectures, continuous functions don't exist in computers. Everything is discrete and everything is approximate numbers. So we need these methods to be able to calculate, for example, the sine or the tangent or the exponential of any arbitrary number. And the computer doesn't only do this with Taylor series, but that is part of the calculation that's used. There are some other methods that are also brought in. We might look at those later. And so when you're in this place of doing numerical approximations, usually Taylor series are part of it. Now, another really important usage of Taylor series, you see this a lot in physics flavored things. So even here in MSc, when we're doing diffraction, which is all about sines and cosines, sometimes we want to approximate those trigonometric functions when we're working with small angles, or when we're doing quantum mechanics stuff and there's a lot of exponentials floating around when we're talking about wave functions, then it might be useful to approximate those, especially if you're working with them on a computer. And the value of doing this approximation is that it makes the calculations faster and it often lets you reduce formulas to forms that look much simpler. And so you can get these really good approximations that are easy to calculate. There's always this trade off between accuracy and pain when you're calculating stuff. So, knowing the first one or two terms in the Taylor series for common functions really gives you a robust toolkit for taking expressions and simplifying them. All right, we've got a few minutes left. So just for, well, not just for fun, but as a fun application of this, not a scientific application, but a mathematical application. If you've seen this before, don't spoil it for everyone else. I actually really love this. This was one of the things that the first time I learned it, it just completely blew my mind. And I was like, oh my God, math can do that? Whoa. So let's do some Taylor series calculations. Let's find sine of x. We go to our formula. I've already done the derivatives here. So we have the function itself. We have the first derivative. We have the second derivative. Notice that negative right there. So sine, cosine, negative cosine. Those are my derivative terms. And we're looking at small angles here. So angles that are close to 0. All right, great. There's our Taylor series for sine of x. Now, if that was too fast and you're like, what just happened here? My real, like, I know this is a very teacher thing to say, but like pause the video and work it out yourself. Take a few minutes or more than a few minutes if it takes you more than a few minutes and go back to the formulas, plug the things in, try it out, see if you can recover this result if you turn the crank yourself. Now, if you are very familiar with this and you're comfortable with it and you're like, yep, I already knew that, great, then you can move on. So I put in my evaluations for the sine of 0 and cosine of 0, and I get this really nice pattern of alternating SIGNs, alternating positives and negatives, and odd powers. This is another really revealing thing about Taylor series is that when we talk about even and odd functions, so functions that have certain symmetries of reflection, that even functions will only have even numbered powers in their Taylor series, and odd functions will have only odd numbered powers in their Taylor series. And so, sure enough, sine of x, which is an odd function because sine of x equals negative sine of negative x, we have third, fifth, seventh, and so on powers in the polynomial. So, that's a really nice thing that comes out and can also help you check your own work if you know the symmetries of the functions that you're working with. But before we go on, I have to go back to those question marks in the title slide. Taylor series, someone always gets credit for an invention. And usually there were a lot of people who contributed to that invention or just straight up invented slash discovered it before the person that it's named after. And Taylor series is absolutely one of those situations. Now, in reality, this fine scholar that I've got named on the slide here, Madhava of Sangramagrama, and if anyone wants to correct my Sanskrit pronunciation, then have at it. But this dude was an absolute genius. Uh, he invented infinite series approximations for a bunch of trigonometric functions in the 1300s. Like Europe was busy dying of plague again, and India was like, "Oh yeah, advanced mathematics, we're on top of this." So, like, I'm not going to get into a whole rant about why history education in the US is garbage. I mean, I'd love to go on that rant, but at another time because I'm looking at the clock. Long story short, um, in the Middle Ages, the Islamic world and India and China were just developing so many innovations in math and in science, and Europe was very late to the game. It's really interesting looking at historical records. This is actually kind of an open question in the history of math is how much were the people like Taylor and Maclaurin and Newton and Fermat, how much did they know about what had been done in the Middle East and in Asia? And were they aware of these previous discoveries? Were they building on them? What were they working with? So, I don't know. Hopefully, we'll find that out someday. It would be really cool. Anyway, this is not a Taylor series. This is a Madhava series. All right, onward. I said this was going to be fun and not just fun because I'm ranting about whatever. Uh, so we'll crank out our series for cosine and exponential. We already did exponential, so that's nice. Here's cosine. I'm not going through the process. I'm just saying here's the answer. Um, this is a typo. I just realized this is a typo. Sorry. X minus x cubed plus x to the fifth. I'm not going to fix that. I'm honest about my mistakes. Also, I'm not going to edit this. Too much work. All right, here's our even powers in cosine. X to the 0, x to the 2, x to the 4. Cosine is an even function. Great. And then here's our exponential Taylor series from before. And if you look at these three things next to each other, they're almost the same thing. There's a very, very close relationship between these. And I said, maybe even on the first day of class, like there's a really close connection between exponentials and trig functions, and we'll come back to that. Okay, we're getting back to it. So here's everything laid out. And this typo is destroying me. X. Sorry about that. I blame myself. Anyway, it almost looks like e to the x equals sine of x plus cosine of x, because we've got 1 and x squared over 2 factorial and x cubed over 3 factorial and x to the fourth over 4 factorial. But there's some positive and negative business that doesn't quite line up. The x squared term is positive in the exponential, but it's negative in the cosine. The x cubed term is positive in the exponential, but it's negative in the sine. But then like the x to the fifth is back to positive again. And so looking at this, you're like, all right, I guess it wasn't actually that great after all. Bye. And that's the end. Okay, no, not really. It's always tough to figure out how long to troll for. Now, here's the answer. Finally, we're getting to it. I know this video is a little bit longer than usual. I hope it has been diverting at times. That is not a typo. So hopefully you see where I am going with this. I is going with this. And think about grammar another time. Put in the square root of -1, because these places where we were missing the minus signs before, those were on higher powers of x. And so if we had a number that we could square and get a negative sign, which we do, that's what I is square root of -1, then that would fix the problem. Because then we would have negative x squared, because I squared x squared, -1 times x squared. And then we get negative I times x cubed, because I times I times I would be -1 times I. And so this gets you even closer to making everything work, because now we have the positive and negative signs in the right places. The only difference is that we've picked up some factors of I on some of these terms. But look at which terms have this new coefficient. It's the first power and the third power and the fifth power. It's only the odd powers. The I has become a coefficient for the odd part of the function, which is the sine part. And that is one of the ways that you can prove this relationship, that e to the ix is cosine of x plus I sine of x. It's not the only way. We're actually going to do another proof sometime later this semester, because this formula is a really big deal. Okay, that's everything I had to say. Thank you for sticking around a few minutes extra. If you have any questions, you know what to do, and I will see you in class.